Well, thank you, Julius, and thanks for the offer to give this inaugural talk of this type. I'm not sure I have the most interesting life, but I'm willing to give it a shot here and see how it goes. Um, as far as my early life, I was born in Harrisonburg, Virginia, which is over in the Shenandoah Valley, for those who aren't familiar with that, and was the youngest of four boys. I have a picture early on of our family soon after I arrived. I was going to make some sort of joke as to things were hard during the Great Depression, but wasn't sure everyone would recognize that as being a joke. So anyway, this was toward the late 50s, and there I am on my mother's lap. Actually, at this time, my father was finishing up a doctoral degree in education, and he went on to be high school principal at various times, college administrator, and a college professor at James Madison University eventually. My mother, after I went to kindergarten, went to work in the registrar's office of our local college and worked there for many years, basically running the office until she took some time off to go back to college and finished a college degree at the age of 60. And all four of the boys there eventually became college professors at various places. So you can definitely say that life in academia was kind of in the cards for me. However, I was the only one in the family who went into mathematics or anything even really close to that. So how did that happen? I think be able to move the pictures that way. Well, my mother, who kept a baby book for me, and I'm always really admire her for doing that the same way for her fourth child as she did for her first child. I think that's really says something. She reports that I had a fascination with numbers fairly early on at age 3.5, and used to occupy myself by just writing down lists of numbers. And in fact, have an example of this that she kept. So as noted there at the bottom, this was at age 4. And as you can see, if you just read through it, it's a sequence of numbers, and I think they're all there. I think it's obvious I learned about numbers before I learned about commas, but hopefully that you can see that this was something that I would do to just kind of occupy my time, especially, to be honest, in church when things were getting a little bit boring. This is what I would do just to pass the time. I also did a bit of calculation at this age, adding numbers together. My mother reports, and this is a quote, at age 4, Larry added on paper from 1 plus 1 equals 2 to 18 plus 17 equals 25, unquote. That was her reporting of that, but I did just want to note here, I think that was her mistake rather than mine. This doesn't go quite that far, but ends up at 25, maybe maybe she misread the numbers there, but anyway, this again was just something that I would do, and also reporting that kind of went from 0 to 10 to 100 and got up to 12 zeros, and I was asking about what those numbers are called at this early age. One other incident from this book that I'll report in writing about one of our neighbor children, she writes, Clay and Larry got along fine, especially when Davy, who was my next oldest brother, only about a little over a year older than I was at kindergarten. When Davy was home, Clay played with him. However, Larry was content. He had other interests, his numbers, for instance. And I sort of think that's the story of my life right there, that who needs playmates when you have numbers? Well, actually, my mother reports that probably after the age of 4, my obsession with numbers, and I don't claim to be any sort of prodigy, it was just an interest of mine, did start to wane a bit as there were other things that I was looking into. In school, I usually did very well in the math courses that I had, and I tended to take whatever was available, the highest courses that were available to someone at my age. At that time, though, I would have to say that to the extent that I was making any sort of plans, I hadn't really considered, say, math as what I wanted to go into. History was maybe more of an interest of mine at that time. And I'd say that continued until maybe my senior year in high school, when I had a course a bit different for high school courses. It was called Intro to Analysis. It didn't have anything to do with analysis at the college level, but I think the idea was that it was intended to maybe push things a little bit further and just see what lies behind mathematical concepts. And I remember in particular one situation where our teacher dropped this bomb on us. I guess I'll have to that sheet here, of claiming that 0.999, if you continue that indefinitely, is equal to 1. And that amazed me, and I recall that as being maybe the most heated discussion that I've ever experienced in a classroom, and not just in a math classroom, just about any classroom. I remember distinctly one of my classmates saying, that's like saying, if I keep giving you 9 apples, you'll get 10. So that's kind of the way that we were thinking about it at the time. And I remember saying to myself at first, this can't be right. But as the teacher was explaining the idea here, it pretty quickly went from there to saying, well, yeah, what else could it be? One way of thinking about it is if they are different, there would have to be a real number that's between them. What would that be? There's nothing that it could be. So again, from that standpoint, I was starting to just have in mind that once you make definitions and think in terms of why things are true, you do have to follow the logical implications of that wherever that might lead. And it was several things, probably around the same age, that that I saw like that, kind of convinced me that maybe mathematics would be interesting and would be worth pursuing. Some of the others, I would say, the uncountability of the real numbers kind of blew my mind when I saw that the first time, but on seeing it, and it became sort of inevitable that that would have to be the case. The existence, the possibility of non-Euclidean geometry, that was another thing that, again, was very surprising at first, but in seeing how it could work, again, it seemed like those were things that, again, you would have to accept if you accepted certain definitions, but again, changed the postulates in that case, of course. So that it was probably things like that that persuaded me to go into mathematics. And by the time I went to college, that was pretty much where I was leaning, what I was leaning toward. The college that I went to was the local college, Eastern Mennonite College over in Harrisonburg. That's we grew up practically on the campus of EMC. So that was kind of the natural place. The very first math course that I took at the college level was kind of a strange hybrid course. It might be most comparable among our courses to the Foundations of Advanced Math course, maybe not quite as high as far as the type of math that we were looking at, but very much in logic and things that could be built from logic. And although that was a challenging course and very much different from other courses that I would have had before then, although the high school course that I mentioned was good preparation for it. That kind of sealed it for me that I was really interested in continuing with math. Other courses that I took at the college level, calculus, of course, and I was quite interested in all of the applications that could be made of calculus. But I would have to say that probably that was never my main motivation in terms of what I wanted to do in math or what interested me in math. It was always nice to see some sort of application that could be made, but again, it was really more the ways in which things were fitting together that that interested me the most, I would say. So it was courses like linear algebra, perhaps, and our course in abstract algebra at the college level that were my most favorite courses, where basically starting from just a few definitions, you can build up to quite a few implications of the results that we have. Now, you might be surprised that those of you who've had my classes before, that not mentioning anything about number theory. Main reason for that is that we actually had no course in number theory, at least at the time. EMC didn't have a course in number theory. The department, I would just have to say, was small, both in terms of faculty and in the terms of the number of majors that I had. When it came to upper level math classes, they might be offered maybe only every other year, even though some of them were required to take for the major. And even in that case, there might be 6 students in class. That was kind of typical of the size of the upper level upper level classes that we had. But I do feel that that I got a really good background, at least in certain aspects of mathematics, from my college experience. When it came to after college, in my senior year, with really no idea really what I wanted to do, I decided to apply to a graduate school, and it was only one graduate school that I applied to, so I'm not saying this is the way to go about it, but with the idea that if I got in, I'd go. If I didn't know what I might be doing instead, but I'd just look for something else to do at that. And I was accepted. This was University of Virginia, and actually got a fellowship for the first year, so that was really nice. But I would and did end up then going off to graduate school right after college, which I'm not sure I would really recommend, or at least for myself. I was probably not at the peak motivation at that point for really continuing with studies, and I would have to say that probably graduate school, that was the one time, at least especially the first couple years of graduate school, first year in particular, when I was really felt like I was struggling to keep up with things, really having more trouble understanding what was going on in the classes, what I was reading outside of class. So that took a big adjustment. But there were certainly times when I considered maybe this isn't the right thing to do. Maybe I should quit at this point or do something else. But I did stick with it, and I would say it may have taken even till my third year till I was really feeling like I belonged there. But eventually that did take place. Now it was at Virginia that I actually had my first course in number theory. And it was a graduate course in algebraic number theory. So there wasn't actually any connection to numbers in the usual sense, at least it seemed that way. And it took me, I would say, all the way through the semester before I was really starting to catch on to what was taking place there. But I did find it an interesting topic, and actually decided to go into number theory to make that my specialty at that time. Now, at least at that time, maybe it has changed. Number theory wasn't really an area where anyone at UVA was doing a lot of research. But fortunately, there was one professor. He was kind of an elder statesman at that point, and not really doing that much research himself. But he was in number theory, and I approached him finally, and was very glad that he agreed to take me on as his advisee. And I would say that I learned most of the number theory that I knew at that time, basically just from weekly meetings that I had with him, when he would just kind of hold forth on things that he knew about, both elementary number theory and algebraic and analytic number theory. So quite a bit of things like that. And so that's how I learned most of the number theory that I know. Now, when it came time to choose to actually work on a dissertation for the doctorate, um, again, I kind of lucked into things at that point. It happened that we had a visiting professor, very young guy, who was particularly interested in the area of elliptic curves, which was a fairly hot area at that time, was becoming hot, and I think it still is. Quite a bit of research that's taken place, open problems that are not well understood there. And so it turned out that I was able to, he had a project that he suggested to me that was really pretty close to cutting edge research. I was able to, with his help, work through that. So I actually ended up with two advisors, I would say, as far as working on the dissertation in particular. Now, just to say a little bit about that topic without getting technical at all, let's maybe here, and I think this was the next thing. So just as a very brief introduction to what we're talking about as far as elliptic curves. Probably the simplest definition is that it's a curve that's given by an equation like this one, usually y squared equal to some cubic polynomial in x. One important thing is that that cubic polynomial can't have any repeated roots, but when that is plotted, here it would be in the real plane, it looks something like this. There are variations on how it can look depending on the number of roots that the cubic polynomial has, but here's basically what it looks like. And it turns out what is good about these from the geometric and algebraic standpoint is that if you draw a line in the plane, it's going to meet this curve at 3 points, exactly 3 points. You do have to make sure that you count them the right way, and turns out that there's a point at infinity that that needs to be part of this. So strictly speaking, you're working in the projective plane rather than the real number. But that being the case, that means if we do have 2 points that are on the curve and draw a line between them, it's going to meet the curve at a third point. And that can be used to define an operation on the collection of points that we have here. And it works maybe differently than what you would expect, rather than saying this intersection is P plus Q. Instead, it's reflected across the horizontal axis there, and the point that in this case is down below that way is what we would then consider as being the sum of P and Q. And it turns out for the people who are in my abstract algebra class, this should be of interest. It turns out that the collection of points that we have this way actually forms a group under this operation, an abelian group, in fact, and it's really that group of points that would be of the main interest. So just had an illustration of the associative property, which in this case is not at all obvious. Let's say here's a third point R for P plus Q plus R. We would then want the line to go through P plus Q and R, and again be reflected across the horizontal axis, come up with what we would mean by P plus Q plus R. Now, just to compare that, on the other hand, if we start with Q and R in this case, that happens to be a horizontal line between those two. Here's the third intersection. Again, we reflect it across to get the actual sum in this case. And then P added to that, so that we get P plus Q plus R. It does end up giving us the same point as we got by the other way of going. So still amazes me that it's true, even though I've seen the proof of this and know why it works. Here, just to illustrate, with the other picture, it gets pretty complicated. But again, we do have that the two lines that are of interest here are intersecting at a point which is on the curve. So that is the main claim of what we have. Now, again, without going into any details, as I was noting, what we're seeing here is really the real number points that are on the curve. From the number theory standpoint, what's of more interest are points on a curve like this that have rational coordinates, rational points on the curve. It turns out that from the algebraic standpoint, that's always finitely generated, but sometimes it actually turns out to be finite. Sometimes it's infinite, but it would have a finite number of generators. That's basically what that terminology means. And questions having to do with that, as to which of those is going to be the case, those are the things that are of main interest from the number theory standpoint as far as elliptic. So I was doing something a little bit related to that with a class of elliptic curves and relating it to objects called modular forms, which won't get into at all. But basically, just to note here, again, this is an important area of research. It ends up having things to do with certain cryptography methods, methods of factoring large numbers. And this was actually just shortly after I finished up with my PhD. Andrew Wiles used the concept of elliptic curves to prove Fermat's last theorem the first time. And that was an ongoing project for many years, but right around that time. So that was kind of like when your college that you went to, if they win the national championship, that's sort of how I felt about elliptic curves being used that way. But again, that not claiming any connection with that. Okay, well, so anyway, that is what I did my research on in graduate school. I came to Mary Washington right out of graduate school. It was Mary Washington College at the time. And continued some research. Now, at the college level at Mary Washington, certainly, I think the main thing that I had to get comfortable with was just the balance of everything that was expected. Certainly, teaching is the highest priority at Mary Washington, as it should be. There are always service obligations, both in the department and in the university or college as a whole. And research, although that's certainly encouraged, does kind of have to take a back seat to that. But I was able to continue with my research to some extent. Got a few articles published specifically on elliptic curves, and that's still an interest of mine, although I haven't done research specifically with that too much in recent years. During my time here, I would say that probably I've become more and more interested in mathematics at the undergraduate level, just based on things that I'm teaching, and trying to find ways of explaining things in undergraduate courses, upper level courses specifically, that maybe are a bit new, or at least are clear to me, and hopefully I can make them clear to students as well. So that has definitely been my concentration, especially over the last 10 years or so. So I'd like to just mention, to finish up, one particular project and how that arose. It actually kind of got started 7 years ago, when I was doing an independent study with one student who actually just needed a course to finish up the math major. And this was a course that we were doing over the summer. So we were taking a look at algebraic number theory, but from the undergraduate standpoint. And so there's a lot of pretty deep mathematics there, and obviously does involve algebraic concepts in addition to number theory. And but anyway, that's what we were looking at. One of the aspects of that area is that quite often you're working with collections of numbers larger than the integers, maybe including real numbers or complex numbers, but subsets of those collections of numbers that have certain properties in common with the integers. To put it kind of broadly there. Things like prime factorization might make sense in those settings. But one of the important things is that what we take for granted, maybe in the integers, the uniqueness of prime factorization, is not something that is always true in that situation. So I think here, share this if I can. Kind of being covered by the Zoom here, but anyway, this would be kind of typical as far as what might happen in a certain setting. In this case, notice that we have the square root of -10. That could be written as square root of 10 times I, but here this is kind of the standard way of writing it. And you can check here, if you multiply out the product that's on the left, product that's on the right, we get that same quantity in the middle. Now, it's not obvious with these numbers, but I'll just claim here that actually the factors that we have on the left-hand side and on the right-hand side can't be factored any further into numbers of the same sort. Now, what's done in algebraic number theory, again, one aspect of it is introduction of ideals then, which again is a concept from abstract algebra, as a way of actually doing the factorization in this case and making it into unique factorization. If we introduce that becomes a way of restoring uniqueness of prime factorization to collections of numbers that have this problem. Well, in working with this student, I hit upon maybe a different notation that could be used for that, actually notation that can be used both for the ideals and for the numbers themselves. And without going into any details about that, on the next slide here is an example of what that notation looks like. And without making any, without explaining this, I'll just claim here that actually this equation, set of equations, is giving the same information as what we have in the equation above. And of course, all of that has to be defined, but here this is the broad idea of what takes place. And then the idea is that expressions like this, they're kind of numerical in the way that they appear. And those expressions can be factored in a way which don't necessarily correspond to numbers, but would correspond to the ideals that we have. So the next slide that we have like this is just an example of how that works without worrying about the second number in each of these. You might notice that basically 14 factors in the usual way, so does 65. And the important thing here is that on the other side, when we do that similar sort of factorization, we do end up with the same factors. That's an illustration of that there is, in fact, uniqueness of the prime factorization that is aimed that way. Well, in seeing this and in working with this more and more after the independent study was completed, I began to see ways in which this could be applied to several other concepts in algebraic number theory, quadratic forms in particular, and without going into any detail on that. And I began to consider whether something like this could be publishable. And with the help of a sabbatical from college, from teaching for one semester, I was able to write up a treatment of this, send it off, and it did end up being accepted and was published only about a year ago. So definitely this is, in recent years, certainly my biggest accomplishment as a mathematician. And just to see it here, this is a copy of the text that was published just a year ago in the Dolciani series of MAA Press. And this is actually pretty good timing because I did want to mention, especially to students who are in number theory or in either level of abstract algebra, that in the spring I'll be offering a topics course on algebraic number theory and using my book there. So that's an example of, again, it really started off with just kind of working with a student here at Mary Washington, but actually did lead to pretty nice result that way. And in looking back at my life in preparing this talk, I realized there were quite a few places where it wasn't really very good planning on my part. I didn't really weigh the options that may have been open to me, but just kind of had some opportunities. And when that happened, I just tried to make the most of them. And I think that's maybe the only advice that I can give. Definitely not saying that my approach is the best one, but I think it has worked as far as my career here. So I'd be glad to take any questions at this point, or Julius, did you want to?
Well, first off, Larry, you blew this out of the pack.
Oh, well, thank you.
Oh my goodness, you just kept me going. This is it. This is what we need. So thank you so much. Thank you.
Well,
You have
thank you.
really
Thank
set a nice bar for the rest of us who are going to come along. And yes, indeed, yeah, we really are grateful. And it's so good to have. Now, you did not get a chance to follow the
you.
discussion
Right,
that was
right.
going on in the chat, but it was phenomenal. So we
Yeah,
do
well,
want.
I'm noticing some names I'm familiar with that
There you
aren't
go.
current students. Yeah, so
There you go.
I do want to check that out. Yes.
Yes, yes. So if I understand correctly, this is being recorded, right, Jeb?
Yep, I'm gonna get the file and I'll send it off to be able to put on the website or somewhere that people can access.
Wonderful, wonderful. Well, thank you so much. I am just thrilled. I'm just thrilled. I can't help myself. So I'm going to turn to others for questions. If you have a question, please, come on in and go ahead, ask your question. This is great. This is really great.
Can I ask a question?
Please.
Larry, how exactly did you end up at Mary Wash? What was the job search like that year?
Oh, again, that was a case where I'm not sure I thought it through that well. So it's actually kind of an interesting story. Coming out of graduate school, I was kind of advised to maybe look at research institutions a bit more as far as where I applied. So actually, I knew there was an ad from Mary Washington, but was kind of dissuaded from applying. But it was getting toward March, April, and wasn't really getting any offers from what I had sent out. And it just happened that I think it may have been that someone who was originally hired backed out. And so it was the chair at the time, Steve Lipscomb, many of you would know, who was kind of at that point just looking for someone, and contacted someone at UVA, and this person thankfully said, well, I know of this person who might be right for that. And so at that point, much later than I should have probably, that's when I actually applied to Mary Washington, and they brought me in, and I was offered the job, and yeah, I'm very glad it did work out that way. Yes.
Yeah, that's pretty exciting. So you applied to one graduate school, applied to one job, and
well,
everything.
I got one job offer at that time. So yeah.
Wow,
yeah.
That's great. That's great. There's a question in the chat. What's your favorite part of being a teacher?
Oh, well, I do enjoy working with students, and I do have to say this semester has been a strange one. Of course, I spend a lot of time just kind of this chair and speaking to people who are sometimes on screen, but quite often not. So
Yeah.
I don't have quite the interaction that I would like, but I'd say that's what I enjoy most in the classroom, seeing that sort of interaction, getting questions, and especially if you can see that something that you mentioned maybe caught on, and people caught the idea behind it. That's probably really what I enjoy most.
Fantastic. Fantastic. There was a question about your favorite course to teach.
Oh, well, let's see. It would probably have to be number theory at this point. But I do enjoy abstract algebra quite a bit as well.
Yeah.
And linear algebra, that I don't teach that as often, but I enjoy that when I have a chance.
Wonderful. Wonderful. Thank you so much. Any other questions?
I have a question. So what are you going to do next? You know, what's your next research? That's always the,
Oh yeah. I really don't know. I mean, in some ways, I'd kind of like to go further with what the ideas of the book, and maybe this was intended as an undergraduate text, and I think that's the main idea. But possibly, I'd want to consider whether aspects of it could be taken further, maybe as research. But to be honest, I mean, this semester especially, it's just kind of a constant staying one step ahead of everything. So I haven't been able to really think much along those lines.
Fantastic, thank you. There's a question that says, if you had to pick a subject other than math, what would you pick? Also known as, what is your second favorite subject?
Okay. Well, actually, I'm not sure if I mentioned, but probably in my early high school days, especially, I think it was history actually that I was most interested in, and that's kind of what I was thinking about as far as the area I might go into again up until that senior class that I had, which kind of moved me in the direction of math.
Wow, that's so cool.
Yeah, so it's not really anything that's too closely connected, but yeah, that's what I was leaning
toward. Right. Wow, cool. Well, any other questions?
There is one more question from Jamie Winslow about what would you tell students entering their college years about choosing math as a major?
Well, I think it definitely leaves you quite a few options, and that's what I would say. I think there was I forget how long ago it was, but we were doing some sort of self-study, and as part of that, I was looking at our website at things that our recent graduates had talked about, and it was just amazing. They were doing all kinds of things, but every one of them said completing the math major, it helped me approach any sort of problem, think through any sort of problem, and so I think that's really important. It's so that I think is what I would say, that really you can do anything with a math major, and from everything that I've heard from employers and that sort of thing, they're always glad to have a math major with that background, especially if it can be maybe combined with computer background or something like that. So that's important as well. I think,
cool.
I think it's always appreciated that.
Thank you, Larry. I see a hand. Matt, is it Matt?
Yes. I'm Martha Cosa, and I graduated from Mary Washington in 1986. And a few days ago, I found out about this from the Facebook group for the math department, which I'm a part of. And I'm really glad that I came to this talk to hear Dr. Lehman speak. I know he started not long after I graduated from Mary Washington.
It was in '86, actually.
Yeah. And I may buy your book if I get a chance to read it, because it looks really interesting.
Yes.
And I still use my mathematics. I went to graduate school in computer science, but I did theory, and the math that I used was discrete math and number theory related stuff.
Right.
And I was torn between going to graduate school in mathematics or computer science, because I loved abstract algebra. That was my favorite class. I liked real analysis too, but I was more drawn to abstract algebra and discrete mathematics and number theory kind of stuff. And I was torn between going to graduate school in math and computer science. I knew math job market was rough. The computer science job market was rough when I graduated too. But I thought that I could have a lot of opportunities and still use my mathematics, being in computer science. And one of my colleagues at Tennessee Tech in the math department, when I met him and I told him my undergraduate degree was in math, that I teach computer science now, he said I went to the dark side. But I don't think I did, but that was a lot of fun. But thank you so much. And I like seeing what's going on at Mary Washington. I grew up in West Virginia and Virginia. I was born in West Virginia, and I moved to Colonial Beach, Virginia, close to Fredericksburg, when I was in 6th grade. And I don't get up that way as often because my parents, when they retired, they moved to Tennessee where I live. And so I miss going up there. I hope to go again. But I visited there and looked around the campus. It's been a while. But I was wanting to ask a little bit about some of my former teachers. Janet and Richard Zalesnock, are they still alive?
As far as I know, the last I heard, they might be living in North Carolina, Wilmington.
Okay.
And I think he's kind of slowed down, but the last I heard, Janet is still doing pretty well.
Okay, good. And Steve Lipscomb was my discrete math instructor, and how is he doing?
He's doing fine as far as I know. Yeah, he still lives in the area. He retired about maybe 12 years ago, or even longer than that, maybe more like 15. But yeah, he developed some sort of engineering thing, and is really making lots of money off that. So he's doing well. Yeah.
Good. And I know Dr. Gary Collier, I saw him a few years ago. Is he still doing all right?
As far as I know, yes.
Okay.
He retired maybe 3 or 4 years ago.
Yes, yeah, I'd seen him some. And anyways, thank you so much. And all of you take care and stay safe. Thank you.
Well,
thank you, Martha.
Thank you.
Yes.
So much.
Martha was our second Oscar Schultz Award winner.
Right.
Yes.
The second one on our plaque.
That's right.
Okay.
Thank you.
Well, congratulations. And
thank you very much.
Yeah, Larry, thank you. And I just want to thank everybody for, participating in this. Melody and Jeb had the heavy lifting piece, and Randall made sure the world knew we were getting together. So it worked. And again, Larry, thank you. You just blew this thing out of the pack. We can see the history part it just came right. As I watched your thing like age 4, I'm going, okay, so where's mine?
Yeah.
So
well, I do have to give all the credit to my mother for saving things like that.
Yeah, this is great. Well, this has been a lot of fun, and we have Dr. Marie Shekels coming up in the spring, so that promises to be very exciting. And you make everybody get really excited. And I don't know about the students, but if I was a student, I would be going, yeah, the math department should have this like every week, So, but thank you so much. And so glad to see everyone here tonight. Thank you, Martha. Thank you.
You're welcome. Thank you.
Coming along. We really appreciate you.
Thank you. Hopefully I'll get to meet you in person sometime.
That's our wish as well. Thank you. And you all have a wonderful evening. And thank you so much. Thank you.